Hi guys, and welcome to this lab. Let me pull the other screen in here if I can find it. This lab has a component that is basically at this point we cannot do it. I mean, you can do it on your own if you want to, and that is to buy the materials to build the motor component of it. So the instructions are actually on Canvas. So hopefully you guys can go through the Canvas, which makes this lab without the construction a lot lighter than a typical what the lab is. So so you guys can basically go through the instructions, and you should be able to do all of the the stuff in the instructions, and we're going to go through that. And then also yeah, that's the only two things. So what we have in here, we have the instructions. It says a FET simulation where we're going to go and actually measure the magnetic field for different configurations, and also draw the North Pole and South Pole for different magnets. I have in here some magnets. This is a magnet that I can, it's color coded usually between the North and the South, okay? And the magnet, I mean, which one you call north, which one you call south is really a matter of convention in here. You can take the compass and which way is pointing, that is actually where it points to is the south of the magnetic pole, because it's north and pointing to the south. So each one of them is color coded, and usually they have the red and but some of them don't have any colors, like this magnet in here, which is actually magnet 2. This is a magnet. Okay, this too is a magnet, okay? And the reason why you see the sharp things is because it's scratching, that's all. Okay, and it touched the, some of them, they have the label north-south, but you can't really, this is also a magnet too. And this one is actually nickel cobalt alloy, which is a very powerful magnet, actually. I really don't want it to get anywhere near the others because it's going to break them or something. And you're going to be drawing the magnetic field lines emanating from the North Pole and dying in the South Pole. So depending on the configurations in that. In the actual lab, if we're doing this lab, instead of actually drawing it by hand, what you get to do is actually have an iron filings, which are tiny magnetized, tiny basically pieces of magnets, very, very thin. It looks like it's pieces of basically, you know, very tiny pieces of iron, basically. They call iron filings or fillings or whatever you want to call it. It's and with a single element too. Anyway, the point being in here is that you put it on a clear surface, usually glass, and then you put the magnet underneath, and then you have the you have a paper, which is a white paper, so that the reflection is perfect, so that you can see the shapes form, and you will see the field lines forming between the north and the south, the north and the south. The key thing in here for magnetic field versus the electric field is the field lines will always terminate. They start from something and terminate, and they go in a circular fashion. Unlike the electric field, which can emanate from the positive charge, but as long as there is no negative charge near it, it can go to infinity. They don't necessarily stop, so they can go toward wherever you're looking at. So theoretically, they have no limit for them. So this is the key difference between them, is one of them actually diverges and goes in a straight line, never stops. And the other one, on the other hand, actually goes in a circular path and come back immediately to terminate. So that is the key difference between the two, okay? Again, let me share with you the instructions so that we see what we have and share. Not screen, I want the actual lab instructions. So obviously, don't forget to put your name. You're going to go through, these are the field lines, the one that, actually this is for an electric dipole, okay? Or a magnetic dipole. If this is a north and this is a south, so this is a magnet, okay? But that's not basically how we're looking at this one. In the case of electricity, this will be the field line. So if this is a positive charge, and the other one is a negative charge, the field lines are actually this. Let me pull a pen in here. So these are the field lines. Oh, Can't I have comments in here too? Comments? No, where is the drawing tool? Sorry about that. This is the highlighter. I hate this new version of PDF. So these are the field lines. And they always comes from the north, they leave the north, and they terminate in the south, okay? So this is their overall direction for the field lines. For a magnetic field. For an electric field, as long as you have a dipole. If it's an electrical dipole, then you have a positive charge and negative charge next to one another. In that case, it's going to behave like a magnetic field in the sense that the electric field will also behave the same thing, but they leave the positive charge and they end up in the negative charge. So that is really the key difference between the two, okay? So this is typically the setup in the lab. And the first question is, single isolated electric charges known as monopoles can exist. However, no magnetic monopoles are known to exist. Magnetic charges can only exist as dipoles with a north always accompanied by south. Why should this be the case? So basically, it's because of a hypothetical. So always magnetic monopoles do not exist, at least isolated by themselves. However, in solid state physics, with the new research that is out there, apparently there is a way of creating monopoles, okay, albeit momentarily, okay, in a local region of space. So in that place, there is actually a monopole, because the other pole is actually isolated from it and separate from it, like you separate the positive charge from the negative charge. I really don't want to confuse you with this one, but I want to say is that in a regular magnet, like the ones I was showing earlier, you cannot really isolate the North Pole and the South Pole by itself. Because if you take this magnet and cut it in half, you will end up always with the pole. When you cut, if this was the south, you will end up with the north on this side and the south on the other side facing the north from the other end. And if you cut from here, the other half and so on and so forth. So technically there are no monopoles, and that is because of the properties of magnets. They come in pairs. So this is the first question. And we discussed this one from actually before the spring break. And you're going to go through this one. So basically what you're trying to do in here, study the behavior of magnets, namely draw the magnetic field and actually measure the strength of the magnetic field. So what I'm going to say to you guys in here is, usually with any objective, leave it toward the end. Once you know what you're doing, then you can come back and write it and write the objective. Again, the rule still applies. The objective has to be at least two sentences minimum, which means it can be more. Please do not list bulleted items. We'll do item 1, item 2, item 3. Try to be verbose. One paragraph, no more than one paragraph, describing basically what the lab objective is and some key concepts that's going to be explored in this lab. Okay, so this is typical behavior for the any objective that we've been doing. Now here is the thing in here for the horseshoe. Let's say, for example, this is the north. So the instructions, if you read them, they will tell you, what is this in here? I don't want to draw a point. I want to draw a line. As a matter of fact, I want to draw the N letter. Okay, so this is north, and I'm having difficulty typing in here. So let me put it with a plain text in here. Can I do it with plain text? Not even that. Sorry about that. This is highlighter. So let's say this is the North Pole, okay? No, I can't do that either. Okay, so let me stop this and then take it from stop sharing. Let me take another one in here, another screen under the problem solving to share with you. Share what I had in mind using this screen. So basically, this is the horseshoe magnet. So if this is north, this is south, the field lines will go this way. You have to be careful in here. It's straight out this way, okay? Straight out this way. and then it starts to bend in here, okay? Because there is actually a region of the magnetic region in here where the magnetic field is more or less constant, something that you're going to be exploring in this lab, okay? So this is one. And then if I look at the other shapes in here, where is the other shapes? What is the PDF file? Cylindrical magnet is just like the one I was showing. Hopefully you guys have the instructions going with you guys. So here is, so assuming the north is this way, that means this is the south. Again, the field lines will leave the north and will go around and come back to the south this way, come back from the south in here, and this field lines will leave this way. So that's what you're supposed to be. You're supposed to be drawing different, basically, field lines for different configurations. So that's basically what you're supposed to be drawing in the first part. So it's just basic stuff in here that you should have no difficulty with it doing it. So this is the first. And then you have two cylindrical. Now you have to be careful with this one in here. So from here, you're looking at one end. So the magnet field lines are coming out, okay? From the middle, for example, and going in from the inside. So in here, if this is a north on this side, the one facing me is the north, then the field line, I'm going to draw them pointy arrows coming out. You know, like this arrow. On the other side, on this side, I'm going to draw the X's with the inside the circles, okay? So that is basically because they are going to go to the south from the other side and come back and go like this. So they're always going in circular fashion. So now we have two cylinders. We have the north on one side, the south on one side, the north from the one side, and the south from the other side. Obviously, this field line can terminate in here. It doesn't have to go all the way here. This field line can terminate in here. This one will come in here and terminate in here. But this one now can go around and terminate in here, okay? But this region in here can be connected together. So because you have two magnets now. So that's basically how you're going to draw this one. Now it's opposite. The field line tries to leave from here and want to end in here. So it's going to leave an end in here. It's going to leave an end in here, but there will be a region of space where there is no field lines, okay? That is a repulsion. So there will be a region of space between them, basically, where the field lines do not cross one another. They terminate in the other one. And the higher that region, the gap between them, the stronger the magnetic interaction between the two, okay? So again, this is typical behavior. You have to be, you can draw this one. If we did this in the lab, and I know you don't have access to a lot of stuff, you will see it actually with iron filings. You will see it, that behavior correctly in there. Now, the field line in here trying to leave and go to this, depending on how big the gap between the two magnets, go to the south pole. As long as these magnets have room for them, they can do that. The minute they are in here, there will be a repulsion again. So again, the region in here, they cannot, the field lines cannot interact with one another. And here again, they will terminate fine from the bottom and from the top, but in here, there will be a gap between them, indicating that there is a repulsion again. Okay.
Person?
Yes, I'm not chatting.
Yeah.
I'm sorry. Thank you for the minute you said it. Okay. So let me, I don't know where I stopped the sharing. Was it in here? Did I discuss this point or not?
Oh, no. Oh,
Okay.
it was that one, yeah. You didn't share that one.
Okay, so basically, the field lines will be coming out and terminating. So let me draw at least some other shape in here from this one in here. Stop sharing and share this one in here. So basically what you have, you're looking at a cylindrical magnet like this from one end. Let's assume this is the north. So the field lines are coming out now. Because we're looking at it from this end. And then they come out and they turn on here. So this will be in here. Obviously, they will be denser near the magnet and they start to weaken because the further you are, the weaker the magnetic field in here. Because the intensity of the field lines also represents the strength of the magnetic field. And so on and so forth. So that is that line that I'm supposed to draw. Again, in this side, and here I have two strong ones. It's going into the screen. And then as I move further away, the density, there will be less and less of them. So there is one far away from it, okay? Same thing in here. There is compact, and it starts to weaken, and it starts to weaken even further, and starts to weaken even further because the lines are far in between. So this is that shape that you were looking at. Since you guys have the PDF file open, so I'm not gonna switch back and forth. I'm gonna stay on that screen. So what I have in here, I have the next one in here. I have two magnets that are facing in the same direction. So this is north, and this is magnet that is also north. So in this case, the field line will leave from here and end up in there. This represents attraction of the two field lines. But then there is something weird in here starts to happen, because this field lines also try to leave, but they will find this ones. And so this interaction is local in here. So around very far away, there will be in here interaction in here too. As a matter of fact, this could flip the whole magnet if there is a strong change one way or the other, okay? Okay, so that's basically how the field lines for the next picture is. Let me look at the PDF quickly here. There is a repulsion on the other side in there, okay? When they are flipped. So this is the north. This is where the north is. So the north field lines try to come in here and terminate, but it cannot because it will find other field lines in here. So it's going to ram into them. And this region in here will be devoured of field lines in here. So there is a repulsion in here, repulsion. The density in here starts to pack in here quickly next to the field lines, okay? So the one that leave in here spaced, now they will become closer to one another in here because they cannot really ram into one another, and this gap stays open, depending on how strong the magnets are, okay? So if you guys have the PDF file open, so I'm going to skip to the next. Hopefully you can follow through with all of these shapes with the north, north, south, south, and you have a bunch of them. So try to imagine the field lines representing the more they are, the stronger the field in there. And they cannot cross one another, okay? They have to avoid one another, okay? And that is basically how the field lines are. And you have so many, you have 10 shapes that you're supposed to do, okay? The next one, let me stop sharing now that file and share with you the PDF now. Share the PDF. So the next one is supposed to be clicking on this one in here. And once the page opens, move to the strength to a value of about 80%. So right now the value, when you open it, I'm not sharing the screen yet, and I know, but I'm going to move the strength to about 80%. Select the show field. Right now it says, when you open it, it says show field, show compass, which is fine. Reposition the magnet so that the field represented by the field lines pass by the middle of the magnet. Reposition the magnet so that the field represented, okay, so I'm going to show you what that means. And then the field meter gives the strength of the magnetic field in Gauss. And Gauss was a unit that we said in lecture that it's 10 to the power negative 4, actually, meaning that it's 10,000s weaker than the Tesla, okay? So B, Bx, By, and the direction theta. The values for the magnetic field are in Gauss. Position the meter so that By is equal to 0. The value of Bx would be equal to that of the magnetic field, the table 1. So here is table 1. So this is basically what the picture is, okay? That you're supposed to be having. So, and you're supposed to fill this one in here, but the position is an arbitrary position actually in units of this arrows in here, okay? So let me do that in here quickly. So let me stop sharing the screen and let me share with you, share the FET simulation. So this is how this looks like when you guys open it. Does everybody see the bar magnet in here from the FET simulation?
Yes.
Okay, very good. So in this case, they said to position the magnet so that more or less it sits in the middle of those tiny compasses, okay? So this is the field line, as you can clearly see. The south or the north of the compass is pointing toward the South Pole. So the compass, the fact that it's pointing to the north, geographical North Pole, that is actually the south of the magnetic pole of the Earth. This is probably something you probably didn't suspect, because the compass has a north and the south. The compass points toward where the geographical north is, where Alaska is, where everybody is sitting in the north. Now, that is actually because it's the north of the compass, it's pointing toward the magnetic South Pole. So the geographical North Pole is actually the magnetic South Pole of the Earth. We need to show the field meter. We need to have this one actually too. And now we have to position it so that By is equal to 0. So if we do it carefully in here, so we're going to have a By that is equal to more or less 0. So because Bx in here is clearly, I mean, look, Bx is 77.52. By is 77.55. For all practical purposes, this is a good position. Albeit there is a silk component for By and Bg and By, which is 2.313 Gauss. So if I position it slightly, now this is perfect. Okay, this is going to be a challenge for you guys. You're supposed to have it. So this is one distance. This is this second distance. This is a third distance. This make the distances in units of this compasses. Okay, these are arbitrary units. And you're supposed to record these values yourself. So this is 1, 2, 3, 4, 5. This is 5 units. This is 4 units. This is 3 units. This is 2 units, this is 1 unit. And at some point, you're supposed to measure it inside, too, okay? You're going to do it on the opposite side, too. This is 1 unit, this is 2 units, this is 3 units, and so on and so forth until you get at least 5 data points, okay? Does everybody understand what they have to do in here? You're supposed to have a By from the field meter, the field meter that is 0, and you're supposed to record the values that you get for the strength of the magnetic field, B that is, because you're supposed to measure B, not Bx or By. You're supposed to measure B, because you would want B to be actually the value of Bx, so you position it so that you check, if you wish, that it is indeed this value, okay? Right now, practically, it's the same value because By is practically 0, okay? And you're supposed to fill out 10 data points on either side of the magnet for your reading. Make sense?
This is while By is still 0.
By needs to stay 0 all the time so that your reading for Bx and B stays consistent, okay?
And that's 10 readings, right?
You need 10 readings, 5 before and 5 after.
All right.
5 on the side of the north and 5 on the side of the south. And there is a question down the road where you're going to go in the middle also and do some reading between the north and the south, somewhere in between that region, okay? Yes?
Yes.
Okay, very good. What happened to the value of B field strength inside the bar magnet? That is what you're supposed to check. You're supposed to check the magnetic field inside the bar magnet. Please vary it carefully. Do not go up and down, okay? Try to stick with the same By value, okay? Try not to have By vary that much. That means you are on the same height. Oh, I had it 0, so, oh man, this is perfect value, okay? Okay, By is perfectly equal to 0. Good luck trying to find the By that is close to 0. You're supposed to tell me what happened to By. B, I'm sorry, in general, the entire magnetic field. Okay. Now you're going to draw a graph based on your data for table 1, graph the strength of the magnetic field in terms of those units for that, basically the units in here for the distance, how far you are. Basically, you have 4 units in here, 5 points in here and 5 points on the other side. Some of them are negative, some of them are positive, and the magnetic field should change from some values and starts to behave. And in here, you're going to draw them in based on your data from a graph, the strength of the magnetic strength, which means it's an absolute value. Okay, strength. It's the how strong it is. So don't tell me that it's pointing south or north, therefore it's negative or positive. No, we're looking just at its strength. Okay, the magnitude of the vector, not the because that's exactly what this device is giving you. It's giving you the magnitude, not the directions. Obviously, okay, you have to be careful with these things in here. Anyway, so we have that. Based on your graph, what is the relationship between the magnetic field and the position? So again, now you're going to tell me, based on your graph, how is the magnetic field changes with direction near a bar magnet, permanent bar magnet. Okay, now we're gonna, the second part, I'm looking at the instructions and hopefully you are too. The second part is to click on the electromagnet, which is this part now, okay? So this is a similar fashion, it's a bar magnet. And why do we have the current going? Can we stop the current in here? No, we can't. I guess. Oh, miss, we can drop the voltage down to 0. Okay, so we have 0 volt. And let's remove this show electrons. I hate this show electrons, okay? So this is for a DC current. For an AC power source, it's going to be slightly different. So you're going to be doing only the AC current. You're not going to be doing the DC current. Because for the other one, it's going to fluctuate. So we're going to do the DC current at 0 volts. It's fine, okay? Okay, select the electromagnet. Make sure the battery is selected and set up the proper environment. So basically show compass and maybe also show electrons. Oh man, we don't need show electrons, okay? But if you want to see the direction of the current flows in the opposite direction, which way the charges are moving, okay? So that you know. Now, position the field meter at about 2 compasses from the center of the electromagnet when the number of coils is 4. So the number of coils right now is 4. So you see here, number of loops, 4. We're going to take this one and position it. Let's turn on the field lines. Position it some 2 values from the center. This is some 2 values from it. Try to keep by also equal to 0 in there, okay? Make sure that by as close from 0 here. Perfect. I landed on it. Okay. So now from the center, and now we're going to read the strength of the magnetic field. So we're going to put this at max, and we're going to read the strength of the magnetic field for the number of turns 4. So the strength is 35.49 for me. So please don't rely on my numbers. Use your own. So you're going to get 3. You're going to get 2. You're going to get 1 loop. So that is basically how it depends on the loop. So you're going to get your numbers in there, and you're going to do them and fill the table 2. So table 2 has all of this data in there. And then based on your data above, does the strength of the magnetic field of an electromagnet increases or it decreases with the number of turns? So in other words, if I increase the number of loops from 1 to 2 to 3 to 4, so it should really, theoretically, it should increase, and you can clearly see it, okay? because as if you have more and more magnets, that's all, okay? But you're going to verify that based on your data. For 4 loops, vary the strength of the battery and notice how this the magnetic field changes with the battery and speed of the electron. Speed of the current is the current, okay? So basically, so we're gonna put it back to where I was before, roughly. And we're gonna vary it from 0 to a little bit, and the more EMF you have, the more current is going to flow. Remember, the charges are flowing from the negative to positive, which means the current is going from positive to negative. So in this case, that's why I really don't like that. So there is a higher current now, the magnetic field is stronger, and so on and so forth. But that is basically, now if it's in the opposite direction, the battery has reversed polarity. Now all that happens in this case is the direction of the magnet direction, that's all. Look at the tiny things and how they change directions, okay? So that is question number 4. And the next part, you can skip it, okay? The next one has to do with a DC battery. I told you guys that this lab is gonna be super short if we don't do the DC battery, okay? So we're gonna skip the second part of the lab because we don't have, unfortunately, the materials for it. That's all the lab. Is it easy enough, intuitive enough? Okay. I have one person who agreed. Sarah, I did not hear you if you're talking.
Oh yeah, I said fine.
Okay, very good, Elizabeth, everybody. Okay, so I'm gonna, if you guys wanna do it later on, that's fine, and very good. So I'm gonna stop the recording first.